We're going to talk today about holomorphic functions on an open set G. And it's important that we talk about an open set because a function might be holomorphic on one open set, but not holomorphic on a different open set. And the intuitive notion on about holomorphic functions is you think of them as very differentiable. And I'll explain exactly what that means in just a second. So let's look at the complex plane, and let's look at the point 0. Look at 0, 0, the origin. So I'm going to look at two different functions that look fairly similar. F of z equals z squared, and g of z equals the modulus of z squared. And I'm going to define z will always be equal to x plus iy. We can always break into the real part and the imaginary part. Well, we're going to see that both of these functions are differentiable at 0, but this function here is a lot nicer. It's more than just differentiable at 0. It's actually going to be differentiable at all points in an open set around 0. Whereas this function we're going to see is only differentiable at 0. If you go away from 0 even a little bit, this stops being differentiable. That's what holomorphic means. If you look at an open set, let's call this the open set G. If you have a function that's differentiable at every single point in here, that's what we mean by holomorphic. So this function will be holomorphic on this open set, but this function will not be holomorphic on this open set because it will actually only be differentiable at this one point. So let's just do a quick calculation. F of z, if we write it in terms of x's and y's, is, you can do this out, x squared minus y squared plus I times 2xy. And so you can use the Cauchy-Riemann. This might be jumping ahead from where you are a little bit. The Cauchy-Riemann equations are, if this is u and that's v, take the partial with respect to x, you get this. Take the partial with respect to y of the second thing. Partial with respect to y, 2x, x is a constant, you get 2x. And note that these two are equal. Similarly, if you do uy, you end up with negative 2y. If you do negative vx, you get negative of something, which is negative of 2y. Oh, look, these two are always equal. So, in fact, since these two are always equal, and these two are always equal, these two are always continuous, because 2x is a continuous function, and negative 2y is always continuous, that's going to be enough actually to prove that it's holomorphic everywhere, since these equations are true everywhere and continuous everywhere. In fact, f is holomorphic everywhere because these equations are always true. You can imagine a situation where you might get 2x here and you might get a 0 there, in which case it would only be true if x were equal to 0. But this is holomorphic everywhere, so it's definitely holomorphic on this open set. And by the way, if we have a function that's holomorphic everywhere, we call that entire. And this function, we can write this as g of z. Let's just write it as kind of what we call the u component plus the v component. Well now all of a sudden we can see that ux is equal to 2x, vy is going to be equal to 0. As I described, this is only true, we need x to be equal to 0. Similarly, uy and negative vx. uy is equal to 2y, and negative vx equals 0. So again, in order for these two things to be equal, they need y equal to 0. At the point 0, 0, both of these are, all these partials are continuous, so we're perfectly fine. So note that this is only differentiable at z equals 0. In particular, it is not holomorphic on this open set because it's only differentiable at one point. It has to be differentiable at every point in order to be holomorphic. Many of the results we see later on this course will require a function to be holomorphic, that's very differentiable. Not only does it need to be differentiable at the point we're considering, it has to be differentiable at the points nearby. When that happens, we say it's holomorphic. Thank you.